everyone. Thank you for the kind introduction. Indeed, I'm here as the project coordinator at the company ReCatalyst, which is a spin-out from the National Institute of Chemistry. It was established in 2021. And today, together with our colleague, Pau, we will present you the project MarketHy. Okay.
So MarketHy is a strange one. Well, let's start with this.
Okay, we could.
Because it is one of the first Horizon Booster projects from the European Innovation Council. This type of projects is basically you get two beneficiaries, two projects that are funded by the EIC on different programs, but in similar topics. And then you take one partner from each and they make you work and do something together and basically start some sort of a collaboration across two different projects. Okay, so I'm representing the University of Galway, but also, of course, the project ANEMEL, as you have seen before. And
yes, our project, which was included in the MarketHy, is called Enabler. It's the EIC transition project. ReCatalyst is the only company in Slovenia that received the funding for the EIC transition. And we were also coordinating this project. Shortly about Enabler. Enabler is actually a consortium project in which ReCatalyst collaborates with Ionisys. It's also a startup from Germany. And with EGPO, they are an industrial partner and end user, let's say, associated to the project. So in the Enabler project, we are developing catalysts with reduced platinum content, which is our flagship product of the company. We can reduce the platinum for up to, let's say, 60%, but it depends also on the end application. And we combine our catalysts with PFAS-free membranes that are developed by Ionisys in the Enabler project. So we took this know-how and the, let's say, business model that we developed for the catalysts in the Enabler for fuel cells applications and adapted in the MarketHy for IM electrolysis.
Yeah, so the idea of MarketHy was basically to try to combine the work that we are doing in ANEMEL in terms of developing electrocatalysts and materials for AM electrolysis, working under these kind of impure water feeds, with what Nina has mentioned about the experience of ReCatalyst to produce a powder catalyst not only at gram scale as in the labs, but at kilogram and multiples, hundreds of kilograms scales that you require to basically reach the demands for green hydrogen production. Okay, so in terms of our role from Galway in this part of the work, we were doing some initial techno-economic analysis of powder catalyst, and basically what we have seen is kind of this situation where you have to consider not only the technical performance, the economics of how you are preparing this powder catalyst, but also considering the environmental effects, because in most of these like newer analyses that are done at different European projects, but also in terms of industrial companies, what we are doing is basically you monetize also the environmental impact of the products that you are producing, and you include that as part of your techno-economic analysis. Okay, so what we have been doing is basically taking up some of our process diagrams on how to prepare catalyst from ourselves in ANEMEL, from ReCatalyst in Enabler, and trying to show how we can go from like the intermediates, the solvents that we need to use, the type of synthetic procedure, if it's low temperature, if it's low temperature, if it's under pressure, if it's just precipitation, and see which are the effects in terms of the economics of the final unit that you get, like a kilogram of the powder catalyst, but also which are the side effects. Okay, so if you have many liters of a solvent that you have to get rid of, this also has a cost, not only economic, but also environmental, and we can monetize this as well. And we can also consider then the reusability and recyclability of the different components that we are developing. Okay, so for that, what we did was an initial kind of assessment using this gate-to-gate approach, where basically what we get is the different, let's see if I can, so the different inputs that you have, and that's one of the examples of one of the catalysts that we are producing in Galway, where we do, for example, inner gas using some sort of diacetamide as a source of sulfur, metal precursors, ethylene glycol, and then what you get is some waste, and you get the final product as your catalyst for oxygen evolution reaction, in this case using what we call this functional unit, that is a very common nomenclature in life cycle analysis for the functional unit of your final compound. And basically what we have is you transport this kind of process or flow diagram into an Excel file to make it simpler, and is where you have basically all your inputs, what you require in terms of temperature, the electricity cost for heating up the reaction, for example, and basically this ends up delivering your cost per functional unit, considering the functional unit as is 1 kilogram of final compound. Okay, you can get this cost that you have for the production of each of the different catalysts that we are producing in Galway and what they are producing here in Slovenia, and be able to compare. So that's kind of the first step, the economics, where you look at how much does it cost to produce this. But then what we wanted to do is also to consider the performance of this 1 kilogram of powder on the application that we are looking at. And that's the work that Praveen, that is here, did in Galway, where basically we took several catalysts that were provided by ReCatalyst. We compared them with commercially available platinum and carbon as a benchmark. And also we compared with one of actually Praveen's catalysts that we have developed as part of ANEMEL as well. And what we wanted to do is not to basically try to reach what Chile's presentation showed at the beginning, to get very low voltages, but what we wanted to do is basically a fair comparison using exactly the same conditions across the different catalysts, okay, using the same type of loading, the same type of deposition of the powder catalyst on the electrode supports, so that we can compare basically side by side which is the performance in terms of the potentials that we are getting based on the amount of catalyst that we have on the surface. And then you can use this data in comparison, in conjunction with the economics to try to reach which is the best performing catalyst at the end. No, because, for example, in the case of the platinum-free, no, the one that we are developing in Galway. Okay, so this has a lot of metals, but none of them are platinum group metals, which makes them much cheaper compared to platinum-based metals. Okay, but then, if the performance of this catalyst is not very, very different from a platinum-based metal, and the cost is half or less, and even the environmental impact of this catalyst is half or less, then maybe it becomes more relevant, even though the performance is worse. And that's what we have been trying to do here. Okay, and also, the idea was to compare this catalyst for the hydrogen evolution reaction only, and then for the oxygen evolution reaction, we prepared also like a typical benchmark, the nickel-iron layer double hydroxide catalyst, so that we can basically only compare the effect of the powder catalyst for the hydrogen evolution reaction. Yeah, so basically we prepared this single cell system in our lab in Galway, and then the comparisons at 1 molar KOH, typical conditions for AEM electrolysis at 3 different temperatures, 30, 45, and 60 degrees. And we can see that comparing the commercially available platinum and carbon on nickel foam, because that's the same as we use for these 3 types of catalysts provided by ReCatalyst that contain platinum and cobalt at different weight percentages. So we can see how they compare versus the commercially available platinum and carbon. Yeah. We have also added here a platinum and carbon on carbon cloth, okay, so a commercially available cathode electrode already, so that we can see which would be the improvement if all these platinum cobalt catalysts were done under the optimized conditions of a deposition on a carbon cloth. Okay, and that's how basically we compare this under the same conditions. And finally, also this high entropy metal oxide that Praveen here developed in Galway. And what we can see here is that at 60 degrees, which is kind of the standard, more or less, temperature for AM, one of the catalysts of platinum cobalt performs considerably better compared to platinum and carbon. And also that the high entropy metal oxide performs not so bad compared to the platinum carbon deposited also on nickel foam. Okay, so these are still kind of initial results, but what we wanted to see is how the comparison, like really side by side between different catalysts with different contents of platinum and no platinum at all compare under the same conditions. Okay. We have also done some stability tests so that we have not only the data at a single point, just activation, and then measure the results and do a comparison, but also we did the kind of longer-term stability test to see if some of these catalysts were less stable or even more stable than the commercially available platinum and carbon. Okay, so here we just took two systems, the commercially available platinum and carbon on the left, and one of the platinum cobalt catalyst from ReCatalyst. And we can see that the stability under like similar conditions is very much the same. And apologies for this kind of shape of the graph, but we had some variations in temperatures in the lab, and it makes it a bit easy. So we have to repeat some of this data. But the kind of the key message that we wanted to provide based on this initial techno-economic analysis is that some of these platinum cobalt catalysts from ReCatalyst are actually performing better than the platinum on carbon that is commercially available. And this has the advantage that the amount of platinum is considerably lower when you have these alloys with another metal. Okay, so in terms of the economics, you have a much better case if you want to get to kilograms or tons of electrocatalyst for applications in AM and even in PEM electrolysis. Yeah, so that's kind of a bit of a summary of this initial techno-economic analysis that we have done as part of MarketHy. Then now I'll leave the floor to Nina.
Okay, thank you. So we complemented the techno-economic with the market analysis, which was based on a 5-step framework. Firstly, we started with the data collection. Then we did external environmental analysis, which consists of Pestel and Porter's 5 forces. We further continued with internal and resource analysis, which is SWOT and RIN. This was supplemented with the insights that we gained through various events and stakeholders that attended these events. And finally, we did a business model canvas in order to create a business model for our company. When it comes to Pestel analysis, probably you are familiar with the methodology, but you have to look at several factors, which are political, economic, social, technological, environmental, and legal. And here we observed several trends. When it comes to political impact, we are all well aware that hydrogen is seen as part of the future energy mix, especially this being supported by several European Union's legislation and also funding, especially from the Clean Hydrogen Joint Undertaking budget. And this somehow feels like a stable environment for IM development and also pilot demonstration. When it comes to the economic impacts, there are relatively ambitious projections done by IRENA when it comes to hydrogen demand. This leads to lower CAPEX and OPEX and strengthens the business case. Further on, the social factors and the impact that hydrogen has in the political and industrial arena seems to be relatively supportive, especially, of course, for the green hydrogen. And there is also some pressure when it comes to policy and ESG mandates. Technologically, currently, as you saw also from previous presentations, we are on average at TRL 6 to 7 systems. And when it comes to our case, we have under development the PFAS-free membranes and non-PGM catalysts as part of the Enabler project. So technology is a near commercial level. Environmentally, of course, the PGM reduction and hydrocarbon ionomers reduce the life cycle CO2 footprint by 25 to 40% versus PEM, and this aligns with sustainability taxonomy that is proposed by the European Union. Finally, there are several policies that support these development trends, and our catalysts fit the upcoming regulations. The Porter's 5 forces show that well, there is a high impact of the suppliers on the IM market, especially due to supply concentration, which leads to also price volatility and dependency when it comes to, of course, the critical components of the electrolyzer stack. Then when it comes to the buyer power, the estimate is that their impact is medium. They have increased technical sophistication, but they have limited supplier choice for IM materials. And also buyers prefer long-term co-development partnerships. There is a moderate threat of new entrants due to entry barriers, which are moderate due to high R&D and IP costs, but there is low capital for small labs and startups. However, in the last years, we saw an increase in public funding, which also helped to lower the entry barriers for smaller companies such as ours. There is a high threat of substitutes. Why? PEM and alkaline electrolysis are already commercial and improving in cost-performance ratio. SOEC emerging for high temperature efficiency, and IM differentiation depends on proving durability and cost parity. The competitive rivalry is increasing also due to all these, let's say, trends in funding policy. There are currently around 15 to 20 active players globally in IM catalysts and membranes, whereas competition is driven by innovation speed, partnerships, and also, as I mentioned, funding access rather than volume. The internal analysis, SWOT combined and complemented with the VRIN, valuable, rare, imitable, and non-substitutable analysis showed, well, that we have to a certain degree some sustainable advantage, especially when it comes to catalyst synthesis and proprietary process know-how, our IP. However, there is some advantage when it comes to R&D collaboration network, which stems from our previous projects, and also the background of the company that is supported by the National Institute of Chemistry. And we have some competitive parity when it comes to scale-up know-how. Maybe if I mention here the opportunities that we still can address, these are the policy push for CRM-free materials. So we now demonstrated the let's say, high reduction of PGM usage for catalysts and remained or improved actually the functionality of the catalysts, but we can now also try to go towards CRM-free. And we have still some let's say, opportunities when it comes to synergies with membrane producers for PFAS-free systems. The threats are mostly focused on fast-moving competitors, which also have, let's say, a stronger background and volatile funding for early-stage hydrogen tech due to, let's say, new development trends which are somehow shadowing, let's say, at the moment, the hydrogen technologies. The stakeholder insights that were gathered by our team show that OEMs see IM electrolysis as cost reduction bridge, but pending durability proof. Suppliers prioritize interface optimization, so catalyst membrane compatibility. The investors want high TRLs before they are willing to fund such technologies. Researchers focused on degradation and recyclability as a next step, and there is, let's say, a consensus that the scale-up is possible if we collaborate and openly share data, which is a challenge if you are working on a commercial market. So the barriers and mitigation strategies which we identified based on the analysis from Galway and our market analysis, we see biggest barriers in durability and stability, where we propose to lead long-term durability testings and development of corrosion resistance non-PGM alloys. Then lack of standardization. So we pledge for EU-wide test harmonization, especially to the Joint Research Council and Clean Hydrogen Joint Undertaking. There are barriers still, of course, in scale-up and manufacturing readiness. So the option is to expand to multi-kilogram scale via modular synthesis. There is still a CRM dependency if we want to reach the KPIs, for example, that are prescribed by the Clean Hydrogen Joint Undertaking. But more and more there is non-PGM catalyst development going into, let's say, higher TRLs and also showcasing better performance. And as another option, of course, is to explore metal recycling and secondary sourcing. The final barrier still persists, and this is environmental compliance. The collaboration on PFAS-free membrane system seems as a right way forward, and we are also working on improving synthesis efficiency and wastewater treatment. When it comes to technology comparison, we did a scan of technologies such as alkaline, PEM, IM, and SOHC. And we see for alkaline that best case applications will be large-scale industrial hydrogen and sites with stable grid power and low electricity costs. For PEM, we predict that the best case applications will be in renewable integration and mobility, refueling, and high purity hydrogen applications. For IM, the trends show that applications are likely to happen in decentralized renewable hydrogen generation, chemical grade hydrogen, and sites that need sustainable flexible operation. Finally, SOHC applications seem to be coupled with industrial waste heat, synthetic fuels, and chemical production and integration with high-temp industrial processes. I'm sure that most of you are aware of the main advantages and key limitations of these technologies, so I will not elaborate further here on these things. And finally, the business model canvas, where I would just maybe point out a few specificities based on the case of ReCatalyst, and what differentiates our company from others. Of course, these are scalable high-performance catalysts for different applications stemming from electrolysis, but also fuel cells and for the production of green ammonia, for example. We are able to transition from PT-based to fully non-PGM due to our already proven catalysts with highly reduced PT content. We have collaborated with PFAS-free and company, so there is, let's say, a validation case on the table, and we already have reliable R&D and validation partners bringing academia and industry. We complement our unique value proposition with a hybrid business model, so we foresee different revenue streams. These are from direct sales, from joint development and licensing agreements, whereas we also seek still R&D funding from EU and national projects. And we offer also technical services and consulting for validation and scale-up. Yes, this would be it from our side. The presentation was prepared by my colleague, our head of business development, who was mainly also part of MarketHy. So I would like to thank to him at this stage. But I'm also available for any opportunities when it comes to EU project collaborations. So I would gladly discuss this further in the break. Thank you.